Okay. Well, Jamie, thank you for inviting me again. It's always a real pleasure to be here and see so many friendly faces, or at least friendly names in the participants list. Almost as good. I'm going to talk today about, it's going to be a somewhat meandering path, but the ultimate goal is to make a few remarks about the measurement problem. Now, I had always thought to myself that I would never utter the sentence, "Hey guys, I've been thinking recently about the measurement problem," or maybe I would say that as a sarcasm, but to actually utter it seriously, I really thought I would never do that, because, well, I've never worked with a measurement problem before. It's always struck me as too hard. None of the extant interpretations of quantum mechanics suffices to my mind to deal with it. And indeed, I've tried my hardest really to avoid anything to do with quantum mechanics my entire career. In my gut, I feel that there's something about the idea of interaction, to take to be a superset of measurement, that we're getting fundamentally wrong, that we just don't understand. Something like the way that people didn't really understand simultaneity before Einstein. But in the past few years, since my work on semi-classical gravity and black hole thermodynamics and quantum field theory and curved space-time, I actually still have I've done my best to avoid thinking about the measurement problem, but I really can no longer avoid it. And so I'm going to tell you some thoughts I have based on actually some rather old mathematical results of mine that at first glance seem, I think, to be entirely orthogonal to the measurement problem and indeed quantum mechanics, because these mathematical results have to do with the structure of classical mechanics. But I think these results really illuminate the ideas of interaction and evolution as they appear in classical mechanics. And they do so in a way, moreover, that makes it very clear how one does not get a similar kind of clean conceptual characterization of an idea of interaction and the idea of evolution in the context of quantum mechanics. So I want to emphasize from the start, I am not going to propose a solution to the measurement problem. What I want to do is, I want to try to suggest a different way of looking at it and trying to approach it, perhaps an attempt to reconceptualize what a good answer to it might look like. So quickly, I'll be talking about, first, reviewing some facts about Newtonian and Lagrangian mechanics and how the intrinsic structure of the dynamics of a classical system actually by itself gives you a clean, perspicuous, and really illuminating both mathematical and conceptual characterization of the ideas of interaction and evolution. And moreover, in fact, as I'll show, or well, sketch, the intrinsic structure of the dynamics actually allows you to derive the entire space-time, the entire structure of classical space-time geometry, which is really rather remarkable. Although I mean, it's remarkable in one sense. If you know the work, if you know the seminal work of Howard Stein on Newtonian space-time structure from 1967, it shouldn't be surprising at all. In one sense, what I'm doing is just making precise and rigorous improvements of the theorem, something that Howard sketched back in 1967, but doing it with far weaker assumptions than Howard suggested. I will then go on to talk about how Hamiltonian mechanics does not allow one to give a similar characterization of neither mathematical nor conceptual of interaction and evolution in the way that is done in the way that is available in classical mechanics. That will then just immediately lead into at that point, a very brief discussion of the state of quantum mechanics with regard to these issues. And correlatively, it will, I think, be obvious that one just cannot similarly derive anything like classical space-time geometry from the intrinsic dynamics of a Hamiltonian system or a non-relative. By the way, the entire talk is non-relativistic quantum mechanics, just to get that out from the start. And so neither in Hamiltonian mechanics nor in quantum mechanics is one have anything available. The intrinsic structure of the dynamics in neither one does anything like determine the structure of classical space-time geometry. And then I'll conclude with a few thoughts and remarks about how, at least to me, what all of this is suggestive of with regard to the measurement problem. Okay, so very crudely, and I'll be able to make this more precise in a little while. But for the time being, let's just start out with the idea of a classical system. And what I mean by that is a physical system that is appropriately, and I'm gonna have to try and move and hold myself just right so the afternoon sun doesn't blast me in the face. So it is a physical system that is appropriately and adequately represented by a space of states that is either an even dimensional manifold or an infinite dimensional manifold if we're doing Maxwell theory. Evolution of the system is governed by Newton's second law. In particular, I mean by that there's a family of vector fields on the manifold that represent all possible dynamical evolutions of the system. And I'll say in a moment what I mean by requiring that these evolutions are governed by Newton's second law. There's an idea of interaction, which in this case means something like applying an external force to the system, an intervention on the system. And there's a distinguished free evolution when the system is isolated, when there are no external forces acting on the system. So again, I have not yet defined any of these things. I have not yet given constructions to show how one can derive them. I'm just saying that this is at least my idea of this. This is the minimum one needs to think about, reason about something that I think is reasonably thought of as a classical system. Let's now begin to dive into the details a little bit and see how the structure of the dynamics actually allows us to reconstruct all of these features of the system. So consider Newton's second law for a free particle. I'm writing it out in somewhat unusual form as a system of first order ordinary coupled ordinary differential equations. But I take it that it's obvious that this is equivalent to the normal, F equals ma second order differential equation. So if you think of the x and the v, and x and v have their normal meaning, x is position, v is velocity, dot is time, is derivative with respect to time. So if you think of x and v as coordinates on the space of states, then x dot equals v and v dot equals 0 defines a dynamical vector field, which has components with respect to these coordinates of v0. The del x vector field, del x component of the vector has component v. The change in the position direction is always v, the velocity. And for a free particle, the change in the v direction, the acceleration is 0. So now let's turn an interaction on. Grab your stick and hit the particle. Well, that changes the equation of motion, but it changes only the second part of the equation of motion, so to speak. X dot equals v is unchanged. Only the v dot components of the equation are changed, and they are changed in the obvious way just by sticking f stick on the right hand side. So we get that the dynamical vector field now has components v f stick And the interaction vector field, and by that I mean the vector field that one had, the vector field that represents the external force, the external applied force, the interaction, is that vector field that one adds to the free particle vector field to get the interacted, that's terrible, but you know what I mean, the interacted vector field. And that clearly has components 0, f stick. And just to look ahead, I hope it's already clear that every dynamical vector field will always have v in the first slot. The x dot component is always v because x dot just is velocity. And the second component is always the acceleration, which is proportional. I'm setting m equal 1 just to not worry about crap like that. The second, component is always the force or proportional to the force. And the interaction vector fields always have 0 in the first slot, in the x slot, and always have the force f in the second slot. And I guess I just pretty much already said what this slide says, but just to recapitulate quickly. So the dynamical evolution is represented by a vector field that always has v for the component of that should be del x, not del q. I guess I was looking ahead to Lagrangian mechanics there. For that part. Interaction is represented by a vector field that always has 0 for the component of the del x part. It points only in velocital directions. So it's an acceleration. It's an instantaneous change in velocity, not instantaneous change in position. And any magnitude of force in any direction can be applied to any system in principle. And multiple simultaneously applied forces sum vectorially. This is what we know about classical systems. Interestingly enough, just as an aside, it turns out that Maxwell fields are classical systems too, which is really rather strange. If you look at the free, can you all see my cursor, or am I just moving this around just for my own pleasure?
We can see your cursor.
Yes.
Excellent. So the free vector, the vector field that you get, the Maxwell equations you get by turning on an interaction, the only interactions that are available in classical Maxwell theory, I'm ignoring things like magnetic monopoles. In classical Maxwell theory, the only interactions you can get are sticking a rho here and sticking a j there. That gives you exactly the same structure. The dynamical vector fields always have 0 curl of E in the first slot, and have a rho and a curl bj in the second slot. And the interaction vector fields always have 0 in the first slot and rho j in the second slot. I'm not going to be talking about that anymore. I can't help throwing it in because I find that so remarkable that they have that Maxwell fields have the same classical structure. So I can now be a little more specific. A classical system is fully characterized. I guess I didn't actually say this before, but I said it implicitly, but not explicitly. It's worth saying it explicitly. I hope it's clear that interaction vector fields have the structure, the family of all interaction vector fields for all possible forces has the structure of a vector space. If you add 2 of them, you just get 0 in the first slot again, and some new force that you can apply to the system. And dynamical vector fields for all possible velocities and forces have the structure of an affine space modeled on the vector space of interaction vector fields. If I subtract one from another, they both always have v in the first slot, so I get 0. And f1 minus f2 for any f is another f, so that's an interaction vector field. So we have Newton's second law. Is completely captured by the fact that the family of interaction vector fields on the space of states has the structure of a vector space, and the family of dynamical vector fields has the structure of an affine space modeled on it. Now I'm glossing over several technical details here. One wants various conditions of completeness and integrability for these algebraic structures that in fact all the classical systems we know and love in fact manifest. But I'm putting all the fine-grained and persnickety mathematical details aside for the purposes of this talk. You're welcome to ask me about them in Q&A if you like. But for the purposes of this talk, what really matters is that interactions of the structure of a vector space, dynamical vector fields, dynamical evolutions, that structure of an affine space modeled on the interactions. And the fully characterized by and the definition will be justified by the theorem soon to come. Now, this definition, I take it, is, as I say, obvious from a formulation of Newton's second law, Maxwell's equations, and the representations I gave of the dynamical vector fields and interaction vector fields. You know, crudely, if I can hit a particle with two different sticks, or I can turn on two separate electric charges currents, I can hit it with both at the same time. The difference between any two evolutions is just the force I need to apply to one to get to the other. And notice that this actually yields a classification of quantities as being configuration and being velocity, as being configuration-like and being velocity-like. I have so far, although I began it with my suggestive talk, with the suggestive example, I began by saying, you know, let's use x and v as coordinates on the space of states. Once I throw away that ladder and just have these vector fields with the algebraic structure, I make no reference to what is a configuration quantity and what's a velocity quantity, what's configuration like and what's velocity like. These algebraic structures actually give me everything I need to classify any quantity you give me, if it's not some funny mixed quantity, you know, some weird mixed quantity like x dot v or something like that, as being either configuration like or quantity like. And that we get that from the affine structure of the dynamical vector fields. Remember, crudely speaking, the vector fields of interaction, the vector space of interaction vector fields always point in velocity-like directions. That allows me to say what velocity-like quantities are, and then I can mod out by the velocity-like quantities and get the configuration quantities. I get that for free from the structure of the dynamics. That I also get for free a notion of a free dynamical vector field, isolation, no applied force, no interaction. That's the dynamical vector field that's distinguished by the fact that only configurative quantities change. And it's once you get technical and precise, it's relatively easy to show that there is in fact a unique vector field that satisfies that property. So again, this slide, I guess, more or less recapitulates what I was just saying. Conceptually, the family of possible interactions allows one to distinguish configuration from velocity quantities in a principled way. Interactions directly modify the system's evolutions only in velocital directions, i.e. generalized accelerations. And by the way, in case you ever wondered, like I did when I first learned this stuff, well, you know, back in the Stone Age, why B is configuration in a Lagrangian formulation of Maxwell theory and E is velocity, I had never had any idea why that was supposed to work. This actually tells you why. If you go back, the B's don't change when you turn on interactions. The E's instantaneously change when you turn on interactions. So E's like configuration, B's like configuration, E's like velocity. So correlatively, the physical meaning of configuration is that those quantities encode the possible interactions the system can have with this environment. And velocity quantities are always dynamical derivatives of configuration ones. And I mean dynamical derivatives in the algebraic sense that's given by the affine structure on the family of dynamical vector fields. So one now has the following theorem that completely characterizes, that shows the relationship between a classical system as I've been characterizing it so far and Lagrangian mechanics. And if you're curious about the 1997/2014, it's because I actually first proved this theorem back in 1997 when I was a grad student in Chicago, and I just never got around to publishing it until I was like 2014. So any grad students or like young postdocs in the audience, do not do this. If you have like a cool result, just publish it, get it out there. Do not do this. So the theorem, given a classical system as I've characterized it, with a space of states S and families of vector fields D and I, one can reconstruct the system's configuration space C from the space of states based on the affine structure of the dynamical vector fields. One can use then the distinguished free dynamical vector field to construct a canonical isomorphism from the space of states to the tangent bundle of that configuration space. Under that canonical isomorphism, the family of dynamical vector fields is isomorphic to the family of vector fields on the tangent bundle that represent all possible solutions to the Euler-Lagrange equation. I call them second order vector fields because if you think that they're the vector fields you get, if you have a vector field in configuration space and you lift it in the natural way to a vector field on the tangent bundle, then those are the second order vector fields. Those are all the possible solutions to the Euler-Lagrange equation. The interaction vector fields are isomorphic to the family of vector fields on the tangent bundle that represent the generalized forces in Lagrangian mechanics. They're the vertical vector fields, one that points straight up and down the fibers, i.e. generalized accelerations. And in particular, the vertical vector fields have the structure of a vector space, and the second order vector fields the structure of an affine space model on it. So there is a sense in which Lagrangian mechanics is exactly the structure of a classical system, one that just obeys Newton's second law as I characterized it algebraically. There's a sense in which one can go in the other direction as well. If I give you a manifold and I don't tell you anything about it, maybe I tell you it's even dimensional, and the manifold admits a formulation of the Euler-Lagrange equation in the sense of having an operator that maps scalar fields to a family of vector fields that has the appropriate structure. And here's where some of the persnickety mathematical details come in. The structure is technically, it's an integrable, complete, almost tangent structure, which for our purposes really is just the affine structure, of the dynamical vector fields of a classical system modeled on the vector space of interaction vector fields. Then in fact, that manifold is diffeomorphic to a tangent bundle. The operator allows one to construct configuration space and to construct a canonical isomorphism between the manifold and the tangent bundle of configuration space that takes the set of vector fields to the second order vector fields on the tangent bundle. And again, D is in particular an affine space modeled on the vector space of vector fields on M mapped to the vertical vector fields on the tangent bundle. So Lagrangian mechanics is very rigid. It defines and enforces configuration and velocity and the difference between them, because what this theorem basically says is that unlike Hamiltonian mechanics, Hamiltonian mechanics is a total slug. You can do Hamiltonian mechanics on any even dimensional orientable manifold. Doesn't have to be a cotangent bundle. Lagrangian mechanics, you must do it on a tangent bundle. And because of that, it defines and enforces the configuration and velocity, the difference between them. It gives you a fixed kinematical relationship between them. The latter is the dynamical derivative of the former in the sense of the affine structure that is defined by on the family of the dynamical vector fields. It gives you a notion of interaction that is distinct from dynamical evolution, and it gives you a distinguished notion of isolation. You get all this for free from the dynamics. So if I know only the space of states as an abstract manifold and how to solve the Euler-Lagrange equation, I can reconstruct everything else. The dynamics by itself automatically defines each of and encodes the difference between configuration and velocity, and correlatively between evolution and interaction, and uniquely it determines isolation. So this is what I mean by classical system. There's a mathematical and conceptual distinction between configuration and velocity that's encoded in the dynamics. There's a mathematical and conceptual distinction between evolution and interaction that's encoded in the difference between configuration and velocity. And there's a naturally distinguished free evolution. In particular, this natural split, this natural divide between interaction and evolution means that there's always a clean separation between a system's degrees of freedom and the degrees of freedom of its environment. No matter what interaction the environment is imposing, so to speak. I know that it's a terrible way to speak, imposing interaction. Interactions go both ways. I'm ignoring Newton's third law. allow me my linguistic abuses here. No matter the interaction that the environment is imposing on the system, I can determine the system's evolution without knowing any details about the environment's degrees of freedom at all, and without knowing anything about the evolution. I don't even have to know what kinds of physical quantities the environment has. Much less do I need to know how those quantities evolve. This, by the way, is looking ahead a little bit, is I think akin to Don Howard's reconstruction of Bohr's notion of classical, made rigorous. And I'll just remark as an aside, it's difficult to see how to analyze general relativity according to these ideas. I don't think, I'm not convinced it's impossible. I just haven't figured out a way to do it yet. And
Erik, sorry to interrupt. This is maybe a naive question, but in the Lagrangian formulation of electrodynamics, when you have E squared minus B squared, E and B seem to enter on extremely, up to a sign, extremely similar symmetric functions. And I just kind of, and indeed in relativity, of course, what's an E field in one frame of reference can become a B field in the other and vice versa, just like any similarly conjugate variables. I think I'm missing something about how one is rigidly attached to configuration and the other not. It seems like.
No, that's a really good question, it's exactly that kind of thing that really confused me when I was back in the Stone Age, when I was an undergraduate and learning E&M, and the teacher just started writing on the board the Lagrangian formulation. And the Lagrangian, you're absolutely right, is symmetric in E and B. But nonetheless, when you do the variation, you treat E as configuration, and you treat B as configuration and E as velocity. And I never understood why. And the reason is, at least the way I now explain it to myself, is that it's only when you turn on an interaction. So here are the free Maxwell fields. Here's a Maxwell field with an interaction turned on. The only allowed interactions are electric charge for div E and electric current for E dot. That's the only allowed interactions, and those change only the equations for E. There's a long discussion to be had about what justifies my writing the Maxwell equations in this way, so that that curl of B becomes part of the equation of motion for E. There's a long story to tell about that. But if
there were monopoles, totally different story.
Absolutely. The story I'm telling works only for like really super classical E&M. No monopoles, only allowed interactions are ordinary electric densities and currents. But that's really the important point, is that the allowed forms of interactions tell you what configuration and interaction and configuration of velocity is. And that is what really encodes the difference between evolution and interaction.
Erik?
Yes.
John, can I ask a question? What about the inverted oscillator?
Don't get all fancy pants on me, Sean.
Fancy.
So, off the top of my head, I don't see why the inverted oscillator would cause any problem for my analysis. It's still the case that insofar as one can write it in Lagrangian form, it conforms to everything I've been saying. One can write.
It's just that the P is and the Q are completely symmetric, even like when the interactions are turned on.
Yeah, that's fine.
Okay.
But again, so since you said P, you're probably thinking Hamiltonian.
Okay.
So let's do Q and Q dot, and for the simple harmonic oscillator, Q and Q dot. Let's ignore all coefficients. So the Lagrangian in this case actually isn't symmetric; it's antisymmetric, but it's nonetheless the case, I claim, that if you look at the free simple harmonic oscillator is just Q minus is just Well, I always get it's q dot squared minus q squared. And then if you, all the possible evolutions are given by all possible interactions with the environment, all possible driving forces. So you just add a generalized force to the right hand side of the Euler-Lagrange equation, and that gives you exactly the structure that I claim one has. So all possible driving forces are all possible vertical vector fields up and down the fibers of the tangent bundle, and then all solutions to the Euler-Lagrange equation for all forced oscillations are exactly the second order vector fields that you get by lifting vector fields from configuration space to the tangent bundle. And all the possible driving forces, the vector fields on the tangent bundle that represent them, do form a vector space, and all the possible dynamical evolutions under all possible driving forces form an affine space model on that vector space. So it works out exactly the same. Is that?
Yeah, that's cool. I see now you want to think about all the possible other driving forces. That makes that change. Okay, thanks.
Sure. So now it turns out that I can use all this machinery. So the full proof of what I'm about to sketch for you is somewhat long, and there's a lot of technical stuff. But I'm just going to sketch the main idea for you. It turns out that in classical mechanics, as I've characterized it so far, evolution characterizes time and its geometry. In a sense, I'll make clear in a moment. Interaction, including isolation, characterizes space and its geometry. And both jointly determine the full four-dimensional flat affine geometry of Newtonian, Neo-Newtonian, Galilean space-time, whatever you like to call it. So briefly, here's how it works. Because the family of dynamical vector fields has the structure of an affine space, the dynamical evolutions, in particular the integral curves of these vector fields, have a natural affine parameterization. That determines the temporal metric, the ratios of the lengths of different intervals in the same curves determined by the affine structure. The interactions determine configuration space in the following way. In particular, what we need to know is how do we show, I've already shown you how interactions determine configuration space. What we now want to show is that configuration space in some way or other encodes not just some Euclidean R3, but encodes the Euclidean R3 that is physical space. So again, just briefly, here's how the argument goes to show that in fact it does. At every point of configuration space, the tangent plane can be naturally identified with the free dynamical vector field, because the system can move freely in all directions at all possible directions with all possible velocities. And in making that claim, I have implicitly fixed a standard of rest, which is the one that determines the stationarity of the configuration at that point in configuration space. The velocity differences among all the different possible directions and speeds that make up the free dynamical vector field on the tangent bundle. The velocity differences among them all correspond to Galilean boosts, the family of which naturally in fact has the structure of Euclidean R3 once the 0 point is fixed, which the implicit frame of reference does for us here. Now the free vector field on the Newtonian space of states, the classical space of states, induces an affine connection on the induced configuration space. Because at each point of configuration space, each tangent vector, each velocity determines a unique geodesic, the one that lifts to one of the integral curves of the free vector field on the space of states on the tangent bundle. It turns out that affine connection, one can show that affine connection is flat. It projects down to a flat affine connection on the Euclidean R3 that we constructed previously. And one can show that it is naturally identified with the canonical flat affine connection on Newtonian 3 space. And Lee deriving that the flat affine connection on Newtonian 3 space with respect to the free evolution vector field, in fact, gives you the canonical flat affine connection on the full four-dimensional Newtonian space-time. So this is, I've have not proven this by any means in the sketch. I mean, I have, in fact, I have written down a precise formulation of the theorem and a real proof of it. I've just sketched the idea behind how it works. But for our purposes, what's really, to me, fascinating and important is that, again, the distinction between time and space is built into the structure of the dynamics of classical physics, as is the geometry of space-time itself. And I mean, the theorem is that the Euclidean geometry of ordinary space, the metrical structure of time, and the flat affine geometry of four-dimensional space-time is entirely determined by the dynamical structure of a classical system. You just start out with the two vector fields, the interaction vector fields and the dynamical vector fields and the algebraic structures on them, and you get everything. It's really incredible. Classical physics is so rigid. You fix the dynamics, and everything else is determined. Just as an aside, just for kicks, I'll mention a conjecture that I haven't had time to really think about, but I think is true, which is why I'm calling it a conjecture. Maybe someone here can prove it for me and save me time. So the affine structure that I got, the flat affine structure, is the reason it's flat is because it is induced by the free evolution vector field. But in fact, it's a bit it's not difficult to show that the intrinsic geometry of the tangent bundle is such that if I pick any second order vector field, any dynamical vector field in the language of Lagrangian mechanics, that actually induces an affine connection on the tangent bundle, and anyone does. Generally speaking, none of them are flat except for the one that's induced by the free dynamical vector field. So if you look at all the affine structures that are induced on configuration space by different choices of conservative second order vector fields, you can't, not just any old dissipated one, you have to stick to the conservative ones. Then all those affine structures are equivalent in the sense that they yield the same geometrized Newtonian gravity space-time, i.e. they're all in the same equivalence class in the sense of Trautmann, related to each other by addition of an appropriate difference tensor to the derivative operator in Newton-Cartan theory. But that is not important for our purposes. It's just kind of cute, and I invite you guys to think about it. Okay, so I think there's been a lot of, I've covered a lot of ground pretty quickly. I think, but almost all the hard work is now done, because it will very quickly become clear that nothing that I have sketched in the context of classical / Lagrangian mechanics is available in Hamiltonian or quantum mechanics. And so I think I'll be able to sketch that very quickly and close with the remarks about the measurement problem in about 10 minutes. So Hamiltonian mechanics, phase space is a symplectic manifold. The family of dynamical vector fields is a Lie algebra that's formed from solving Hamilton's equation for all Hamiltonians. The only fixed relations between the Q's and the P's are the canonical Poisson brackets. And here note that the Q's and the P's really are symmetrical. In classical / Lagrangian mechanics, we could distinguish configuration from velocity because velocity is the dynamical derivative of the configuration, where dynamical derivative is defined by the affine structure on the family of dynamical vector fields. We have nothing like that here. Nothing in the dynamics allows us to distinguish the Q's and the P's. The Q's and the P's enter the dynamics entirely symmetrically. And what's worst of all for our purposes, interaction here just can only mean adding another Hamiltonian. In other words, the interaction vector fields are the same as the evolution vector fields. One way to make this precise, and unfortunately this theorem is not nearly as perspicuous as the other theorem, but if you think about it for a little while, it actually does say what I claim it says. And it's a real bear. So maybe I'll just let it go and to save time, and we can come back and talk about it during Q&A if you want. But just trust me. It really is the case that you cannot distinguish the Q's and the P's, and the interactions and evolutions really are the same thing. When one simply restricts oneself to the dynamics. The dynamics does not allow one to distinguish them in any way whatsoever that one had available in classical / Lagrangian mechanics. So one upshot of this is that Hamiltonian mechanics is not a classical framework, not in my sense. The families of evolution and interaction vector fields are identical, both having the structure of a Lie algebra. There is no principal distinction between configuration and momentum. In particular, the latter is not the dynamical derivative of the former, and their fixed relations are symmetric. A fortiori, there is in fact no naturally distinguished free evolution vector field. The zero vector field is not a good candidate. It's the only one that really is you might want to pick. It's too degenerate. One wants to allow constant changes to configuration for free evolution, but there's no such thing in Hamiltonian mechanics. So if I give you a manifold and I tell you how to formulate Hamilton's equation on it, so all I have to do is give you a symplectic structure. So if I tell you the structure of the dynamics, you can't tell me what's configuration and what's momentum. You can't tell me what's spatial versus temporal derivatives. You can't distinguish interactions from evolutions. You can't tell me what interventions are. And you can't tell me what free evolution is. There is no clean, again, if all I do is give you the dynamics, I just give you the symplectic structure and the family of scalar fields of all Hamiltonians. There is no clean separation between a system's degrees of freedom and those of its environment. I need more information. If I want to know what an evolution is versus an intervention versus an interaction, if I want to know what isolation is, I need external information. In effect, I need to be able to, I need to reach in by hand and fix, and there are various ways available of doing it. Fix what's a Q and what's a P. What counts as an evolution and what counts as an interaction. Well, I mean, but by the way, I hope you guys don't mind. I need 5 seconds to go close my back door because it was such a beautiful day, but it's starting to get chilly. Okay. So why then does Hamiltonian mechanics work so well to model classical systems? Well, because by fiat, we identify some variables as momentum and the others as configuration. We then restrict attention only to Hamiltonians having a very special form, those that are purely quadratic in momentum. And this then, it turns out, reproduces the fixed kinematical relations between configuration and velocity in classical systems, that the one is the dynamical derivative of the other. So if you think about, so the standard simple harmonic oscillator, this yields the correct classical relation, V equals Q dot under the Legendre transform. But think about, P squared plus Q squared plus P, which one might want to think of as an attempt to represent a dissipative system in Hamiltonian mechanics, but doesn't really work. That's not a classical system because it doesn't have the correct classical fixed relation between V and Q. You get V equals Q dot plus 1, which is physically meaningless. And if you think about H equals P to the 5 halves or H equals sine Q, then things are even worse. So Hamiltonian mechanics is not a classical system. We shoehorn it into the classical framework because it turns out to be incredibly useful computationally to do that. But its intrinsic structure is not classical. And so I imagine you can already, y'all will now already know what I'm going to say about quantum mechanics because I basically said it all with regard to Hamiltonian mechanics. The situation is essentially the same. Dynamical vector fields are unitary flows on Hilbert space, evolutions. Unitary flows are exponentiated Hamiltonians, self-return operators. Interaction is just adding another Hamiltonian. There's no distinction between evolutions and interactions. The only fixed relation between configuration and momentum is the canonical commutation relation, which is entirely symmetric between the Q's and the P's. In other words, if I just give you the family of evolutions, i.e. also the family of interactions, and I give you the canonical commutation relation, you can't tell me what's configuration and what's momentum. Nothing in the dynamics allows you to tell me that. The families of evolution and interaction vector fields are identical, forming a C-star algebra. There is no principal distinction between configuration and momentum. In particular, the latter is not the dynamical derivative of the former, and their fixed relations are symmetric. A fortiori, there's no naturally distinguished free evolution vector field. And again, the zero vector field is not a good candidate for this. So if I just give you a Hilbert space and its family of self-adjoint operators, if I give you the dynamics, you cannot tell me what's configuration and what's momentum. You can't distinguish interactions from evolutions, external interventions, such as measurements, and you can't tell me what's free evolution. So again, there's no clean separation between the system's degrees of freedom and those of its environment, in the sense that in order to tell what free evolution is and therefore what interaction is, I need more information than just the internal dynamics of the system. This is akin, I think, to Don Howard's reconstruction of Bohr's understanding of entanglement, by the way, and his insistence on Bohr's insistence on complementarity in quantum measurements, made, I think, rigorous. So again, you might ask, how do we in fact distinguish the Q's and the P's in quantum mechanics and so define a free evolution? And I claim we do it in one of two ways. So these are the two ways that I know of. One, just by fiat, we just, by ostensive definition, as early Carnap would have it, those are the Q's, those are the P's. Or else we introduce a representation of the Poincaré of the Galilean group, a la Wigner, and define Q as the generative translations and so on. In both cases, we must explicitly and by hand hook the dynamics up to the background spacetime structure to get a principal distinction between configuration and momentum, and so define what we mean by free and what we mean by interacting. We have to the dynamics by itself, the intrinsic dynamics doesn't give this to us. We have to reach in by hand and hook it up to a spacetime structure that we have in some other way characterized. Wild speculation. Perhaps the lesson is that there is at bottom no real difference between Q and P in quantum mechanics, which would strongly suggest that quantum gravity should not be formulated in a 3+1 framework. That's just by the by. So where does this leave us? I don't know. Here are the possible responses. And we can modify quantum mechanics or look for interpretations that make differences between evolution and interaction clear, as in classical mechanics. And this is, I think, implicitly what is done, in fact, in most, if not all, common approaches in popular interpretations. In many worlds with a bird basis, Bohm, GRW. It's not really clear to me. It's not really clear to me about information theoretic, what the status of this is with regard to information theoretic approaches. But the point is that all the popular interpretations all the kind of popular standard, well thought about, well worked over interpretations of quantum mechanics and approaches to the measurement problem always assume that there is a clean conceptual mathematical distinction between the idea of evolution and the idea of interaction. I claim that we perhaps shouldn't be so quick in allowing ourselves to assume that. That is, I claim, what my results and my arguments, I think, very strongly suggest, is that this distinction is a deeply classical, this is really something from classical physics. This is something that lives naturally, arises naturally in classical physics. This is not something that arises naturally in quantum mechanics. We force this distinction into quantum mechanics because that's what we've always done in classical physics, not because it arises naturally from the dynamics like it does in classical physics. So as I say, the first possible response then is to modify quantum mechanics, or else to look for interpretations that make the difference between evolution and interaction clear here as it is in classical mechanics. Second possible response is to reconceptualize interaction in quantum mechanics so as to accord with the facts that, as I've mentioned, as I've laid them out. The third is to get rid of the distinction between evolution and interaction altogether and reconceptualize dynamics. There may be other possible responses. These are the three that occur to me. One just smells wrong to me. It doesn't take quantum mechanics seriously enough in and of itself. It would be like Einstein worked out special relativity and then said, screw it, this is too weird, I'm just fixing a preferred frame. Two, I think, is just still too conservative, at least for my taste, given the experimental and mathematical facts. So maybe we wait for our Einstein to implement three. Thank you.
Okay, well, we've got a lot of questions already. Shall we start with Peter?
Sorry, I asked my question.
Oh, okay, sorry. Well, then let's go with Jeremy.
Erik, thank you very much. There's so much to ask about. I just confined myself to a simple one. The gist of the discussion of the Lagrangian and Hamiltonian is that the interaction vector field is like 0 in the first slot, and it only points in the velocital directions, reflecting second law ideas. Instantaneous acceleration, but no change in the configuration thanks to a force.
That's right.
And I totally see the contrast with the even-handed Q's and P's of Hamiltonian. And I accept that the quantum endorses Hamiltonian. I mean, in fact, the QP relation becomes a Fourier transform, which is just a unitary basis change.
Exactly.
But I distinguish being unable to characterize interaction as it's ambiguous. I mean, there is a sense in which in quantum or in Hamiltonian, one can perfectly characterize lack of interaction. It's the zero, it's having the zero interaction Hamiltonian, right? What one should say is that the meaning you mean when you say one can't characterize interaction or distinguish free evolution and interaction and so on is something along the lines of the basic concepts don't have any analog of what you emphasized is there in the Lagrangian case, that the interaction vector fields point only in velocital directions.
So for me, you're absolutely right. There is an ambiguity in the claim that I tried to disambiguate, but perhaps I didn't do it entirely successfully. So when you say that, of course we know what it means for there to be no interaction in quantum mechanics. It's just the free Hamiltonian. So let's say p squared over 2m. But my question is, well, yeah, I mean, well, my first response is, yeah, of course, that's the free Hamiltonian. We all know that. But where do you get the p from? That's my question. And you get the p from either, I claim, by fiat or by implementing a representation of the Galilei or the Poincaré group, a la Wigner. So you don't get it from the dynamics.
Yes, sorry.
And the difference, again, from the classical case, is that one has built into the mathematics, just staring you in the face, that the interactions and the evolutions are different families of vector fields. And in quantum mechanics, they're not. They are interactions and evolutions are, insofar as one can talk about them, are both exponentiated Hamiltonians. There's no distinction between evolution and interaction. If I just give you a Hamiltonian for a system in some weird basis, and I say, split, I don't tell you what the P's and the Q's are, but I just give you the Hamiltonian in some weird basis, and I say, here, split it up into free and interaction. You can't do it.
Yeah, well, I'm going to resist following up, Jamie, Thank you, Erik. I'll write you an email on the follow-up.
Thank you.
Okay, Jacob.
I have about 100 questions, so it's going to be hard for me to pick just one.
Awesome.
Maybe I'll ask just one right now, and if there's time permitting, I'll ask others, or maybe we'll communicate offline with Erik.
I was gonna say it sounds like you and I need to have a private Zoom.
Right. Yeah. Yeah. So yeah, and I recently read your 2014 paper, so this is all very fresh in my mind. It's fantastic. So I highly recommend everybody to read that because the details are really absolutely beautiful. So I guess the question I wanted to ask first is, to what degree are you taking second order dynamics as a bare posit, as a brute fact about what you mean by classical dynamics?
I am taking that as an absolute bare posit.
Okay.
In the following, no, I want to take that back. It's not quite right. It's not a bare posit. It's something I claim that we figured out, that we, that me and Newton, that it's something that Newton figured out, but by empirical investigation. He in somewhat anachronistic, but I think entirely accurate terms, what Newton discovered is that in order to be able to predict the future evolution of a system from its present state, he needed to know its configuration and the first derivative of its configuration. And with that data, he could, and of course, knowing what forces would act on it in the future, he could predict its future. If he knew only configuration, or if he knew configuration, first derivative, and second derivative, then he couldn't consistently predict things. But if he knew exactly configuration and first derivative, he could predict things. So in other words, he discovered that classical physics is second order.
I guess I have a very quick follow-up to that question. You already indicated in your talk that there are some ostensible systems that we might characterize as classical, like electromagnetism with both electric and magnetic monopoles, that are sort of difficult to fit into this story, at least in an obvious way. And I guess the question is, what about systems where you've got back reactive feedback interactions, like a charged particle accelerating an electromagnetic field, where you've got like Abraham-Lorentz forces and potentially not a well-posed second. I mean, those appear to be empirical systems, at least to the degree to which we take classical physics to be empirical.
Absolutely.
So is this framework too rigid to actually contain all of classical physics?
In the sense,
in a way, are we kind of doing what can sometimes happen in like algebraic quantum field theory, where we prove all these theorems and say all these things about field theories, but they don't end up being general enough to accommodate, at least as far as we understand, phenomenologically interesting field theories?
So I think that the issue of something like the Abraham-Lorentz force is, to my mind at least, conceptually unresolved. I actually don't know of any. I know of lots of problems in say the mechanics of rigid bodies, where it's computationally incredibly convenient to do things like take what are they called, these higher moments, the higher derivatives of position. They're called like the jerk and the kick, and where it's incredibly computationally convenient to do that, but fundamentally at bottom it's still a second order system. So I don't know of any example where things are definitively solved, where what I would want to call a classical system can't be handled as a second order system. I'm open to it, but insofar as at least what I mean by a classical system is second order, then all this stuff goes through. But I agree, there's a very interesting discussion to be that needs to happen there. I think you're absolutely right.
Thanks. I'll go to the end of the queue now if it's okay, but I'll leave my hand up if that's all right.
Absolutely. Now I think Enrique says he has a finger on this one.
Yes. Hi, thanks, Erik. Fascinating. I'm just wondering, since you're restricting yourself to second order, and we have a duality in terms of the Legendre transform between the Hamiltonian and Lagrangian, what is wrong with just translating everything to the Lagrangian, identifying what is what, and then translating back to the Hamiltonian. Couldn't I consider that to be something, in a way, an operation that I'm identifying the configuration momenta inside the Hamiltonian framework?
The problem there is that works only when you restrict. So there are at least two issues. The first is that really works only when you restrict, I claim by fiat, although very empirically well supported and incredibly useful and fruitful fiat, the class of allowed Hamiltonians to those that are quadratic in momentum. Now, that's on the Hamiltonian side. On the Lagrangian side, you're going to lose all of the dissipative Lagrangians. So H equals Q is a perfectly consistent, well-defined Hamiltonian system. It's a boring one, but L equals Q is not a consistent. I'm sorry, L equals Q actually is consistent, but L equals Q dot is not consistent. I think that gives you 1 equals 0 if you plug it into the earlier Lagrange equation. But H equals P is not only not inconsistent, it actually is arguably the Hamiltonian of something that we all know and love, which is the photon. So there are, things like H equals sine Q. Well, it's a Hamiltonian that no one in their right mind would ever seriously consider as representing a real physical system, but it's a perfectly good Hamiltonian. But there's no Lagrangian correlate, and in the same vein, any dissipative Lagrangian, there's going to be no Hamiltonian correlate. So the only reason why Hamiltonian mechanics works so well for modeling classical physical systems is because we just say, I'm only going to use the very restricted set of Hamiltonians that give me classical behavior. But nothing intrinsic to the dynamics of Hamiltonian mechanics itself demands that. But in Lagrangian mechanics, it's just built in from the start that Q dot equals V. You must have Q dot equals V in Lagrangian mechanics. You don't have to have Q dot equals P. I mean Q dot equals V, or the correlate of Q dot equals V in Hamiltonian mechanics.
Erik, can I just ask, can you phrase this story in terms of knobs? That the Lagrangian formulation has exactly the right knobs, that when you turn them, you generate exactly what you want, but the Hamiltonian picture, you change the knobs, and now you've got knobs that give you totally non-classical systems?
Well, it sounds like you just did it for me, so thank you.
Okay. I had this conversation with Jill North, actually, about knobs of different frameworks, and we like the Hamiltonian knobs because they let us mathematically reformulate things and make problems simpler to solve.
They're incredible.
But they may be the knobs that screw up.
Hamiltonian mechanics is absolutely wonderful. All glory to Hamiltonian mechanics for being computationally just so simple and easy. It's just not intrinsically classical, I claim.
Okay, next up on my list, I have Sean.
Oh, thanks. So actually, that was half my question was just answered, but I do have another half, which is about. So I mean, at the quantum level, you also have the state that you want to call a vacuum, right? And I think in quantum field theory, it's even more like there's more ambiguity about what that state is, and it seems to me that choice that you make does single out what the free Hamiltonian should be. So I thought maybe
I think that's exactly right. So this is all, since as I mentioned at the very beginning, I really got forced, kicking and screaming, being dragged all the way to think of the measurement problem by my work in quantum field theory and curved space-time. And so I thought that it might be best for me to start out not just to dive headfirst to the deep shark-infested waters of quantum field theory, but to see what I could do in non-relativistic quantum mechanics, which is already hard enough. But now that I worked out something that is at least a way to get a start on some ideas here, I have started to think about quantum field theory, and what you say is to my mind exactly the natural starting place to try to start generating arguments of this and observations of these kinds. So I think you're exactly right. So
Okay.
it actually is very encouraging to me to hear you say that, because that seemed to me to be exactly the right place to start in QFT.
Cool. I also want just to make, like, there are Lagrangian principles that can handle dissipative systems. There's something called Herglot's principle.
But you mean Hamiltonian?
No, they're Lagrangian variational principles that.
Oh yeah, absolutely. Absolutely. That's what I hope I didn't misspeak earlier. But what I meant to say earlier was that one has dissipative systems that one can handle very naturally in the Lagrangian framework that one cannot handle in the Hamiltonian framework.
Oh, sorry. Okay, but you also have contact systems. I mean, the Hamiltonian point of view, you don't have to use symplectic manifolds.
But well, of course, one can do generalized Hamiltonian mechanics with in odd dimensional spaces and context structures, but then you're changing the rules of the game as far as I'm concerned. Those are very, very interesting dynamical structures to consider. But I claim that doing that at least doesn't help you with regard to at least the kinds of questions that I care about. It's not generalizing in that kind of way is not going to allow you still to tell me what the Q's and the P's are.
I'm not completely sure, because when in a dissipative system, it's the P's that are often losing energy. But I don't have a definite answer for you, but I'm not 100% sure that's still true.
But the reason you say that is because you're thinking about energy as being quadratic in momentum.
Yeah. Okay.
Which means you already told me what momentum is.
All right. I'll shut up.
Okay. Next on my list is Brian. Thank you.
Fascinating talk, Erik, and I've benefited some from the fundamentality of the Lagrangian that's overlapped with some of my interests as well. One thing you didn't say much about, however, is general relativity. So on the one hand, I was nervous about your even dimensional manifold, because if you want to represent time-dependent, velocity-dependent gauge transformations in general relativity, which of course you do, then you'll want to have time cross something or other. So I'd prefer to add, +1 to your manifold aspect. You did say that Maxwell's theory, however, counts as classical by your reckoning, and there are certain mathematical analogies between GR and Maxwell. So I'm curious, I haven't tried to work it out in your framework. Does GR count as classical within your framework?
That's no, it doesn't, at least not straightforward. So the problem is I haven't even been able to figure out how to pose the question for GR, because there's a certain sense in which when I make the claim that that Lagrangian formulation of Maxwell theory makes it fit naturally into this characterization of a classical system that I've given, that really only works because there are in fact two sets of independent variables that one even has the possibility of asking the question, which is configuration and which is velocity. But one doesn't have that in general relativity, although the Lagrangian just is the scalar curvature. But although now that I say that, maybe it just a thought occurred to me. Maybe you could use the Palatini formulation, and maybe like the metric would be, I guess the metric would be maybe velocity, and the affine structure would be configuration. I don't know. I'm just now I'm really just pulling ideas out of my ass and speculating. But I think that so the short answer is no. General relativity is not a classical system in my sense. At least I have not been able to figure out how to massage it or reformulate it so as to be able to fit it into this frame, to fit it into the framework. And that actually, I guess, isn't terribly surprising to me, because part of what it means to be a classical system is that there is this fixed kinematic, that there's a canonical idea of what it means to be a configuration. There's a canonical idea of what it means to be a velocity. and there's a rigidly fixed kinematical relation between them. And one just doesn't have that available. And in fact, one doesn't, as you know, Ehrman showed back in the 70s, and I think people really haven't actually looked at this. It's an incredibly fascinating, people haven't looked at this enough. It's a really fascinating case study. If you look at just parabolic fluid mechanics in special relativity, you lose the canonical, you lose that fixed canonical relation between configuration and velocity. So already there, it looks like things you're losing a kind of fixed, you're losing this fixed relation that is intrinsic to classicality. So yeah,
So even though GR is a Lagrangian field theory, that is a broader concept apparently than your notion of classicality.
that's right.
Thank you.
Anna? Did I pronounce that correct?
Hello, can you hear me? Yeah, so sorry, my name is wrong here because I was using a different machine. My name is Carlos Zapata, and I just a couple of years ago.
I'm sorry. Can you please repeat your name more slowly?
Carlos Zapata.
Okay, got it. Thank you.
Yeah, so I finished my thesis a couple of years ago on precisely the formulation of phase spaces, and I found your talk super fascinating. I think it aligns a lot with the ideas I was having there. So I guess I can give you a perspective on a quick finger that was pointed out about contact manifolds, but also on this idea that Hamiltonian is somehow fundamentally different from this Lagrangian business or this classical physics business that you're presenting. Because I guess, so I have a question about this, because I think when you say, where does this leave us? I had thoughts about that, and maybe you want to tell me what your thoughts are on this. But basically, the way I view Hamiltonian mechanics, and by the way, I do Hamiltonian mechanics on contact and pre-contact, and for me, it's very general. In fact, Dirac structures on Courant algebroids is enough for me to really mean Hamiltonian mechanics, and it all boils down to the same thing. It's what I call a Hamiltonian phase space theory, and in my view, they are these theories that are specific to observers, and so they're identifying measurements and they're describing dynamical systems in this sort of experimental way. And so what really matters is the fact that you have some observables, and the phase space just generates the algebra of observables, and what you work with is the algebra of observables. So in some sense, we're not. It's not a theory of observers, so it's not really a theory of physics in the proper sense, because you're not intending to immediately communicate between observers within the theory. So it has a lot of prediction to say, okay, the dynamics will take the system to this later place in time, and I'll have predictions for that. But it hasn't a built-in structure for communication between observers. That is in the Hamiltonian picture, regardless of the mathematical structure that you use for it. So I think that in the Lagrangian case, or the classical physics case, that I never really fully understood, and I think your talk is a very good introduction to fully understanding it, in my opinion. This thing is conceptualized in the affine structure, and it's given some extra components to it. So my question, or my suggestion, or I don't know, speculation was, could you imagine having a similar algebraic formulation in the same way that we have all this algebraic formulation of Lie algebras and the whole integration theory for Lie algebroids and Lie groupoids and this kind of thing, for the case of classical theories, and extending to the quantum question, quantum physics question? Could that mean that you will be able to find something like a quantum relativity that has no connection to space-time relativity?
So I think that's a really interesting question. I mean, I'm sorry to say that I'm not familiar with your own work. Please email me some references. I would very much like to see that.
Yeah, I was going to say I'll email you and we can. Yeah.
With regard to the very last question you asked, not only is it, I think, possible, well, it's okay. In a Pickwickian sense, it's already been done by among others, Klaus Landsmann. I'm not sure if you're familiar with his magisterial book that can also be used as a weapon, the Foundations of Quantum Mechanics book. But the reason why I say so he does give a completely algebraic formulation of classical physics there. The reason why I say it's Pickwickian is because he kind of cheats in my mind, in that he's really doing Hamiltonian mechanics behind the scenes. and he's not really giving you an algebraic formulation of Lagrangian mechanics. And I think it should be possible to do. I've never thought about it seriously, but my very strong suspicion is that it should be possible to do. But that's only my conjecture.
So just a very brief point. Is it then correct to interpret your talk as saying that what's really different from classical physics is that there is some information about communication between systems or communications between observers, depending which picture you're taking?
Well, so that's one way of formulating it. Is that to my mind, one of the things that's incredibly fascinating about classical physics is that you can completely encapsulate and isolate, not in the sense of conceptually isolate, the dynamics of a classical system from all knowledge of the rest of the world. You don't have to know anything about the rest of the world, anything about what kinds of physical quantities it has, anything about how those quantities evolve. You don't have to. You can know jack about it. All you need to know is how the rest of the world changes the values of your classical system, and you can do everything you want to with that for your classical system. Quantum mechanics doesn't work that way. You need to know what the environment is like, what physical quantities the environment has, how those physical quantities evolve, if you want to figure out how your physical system evolves. So yeah, I think that's a very fruitful way of thinking about it.
Okay, great, thanks. I'll email you. Yeah.
Thank you.
So I did have Harvey next, but I think he's unfortunately had to leave. So last on the list was Dan.
Yes, hi, thank you. So thank you for the talk. It was really nice. So my background is more in algebraic quantum field theory on curved spacetimes, and so
these are my people.
Okay, so in this context, the Hamiltonian formalism is not really well, let's say the obvious formalism to use. If it even can be formulated without, if you don't have a Killing vector field. But it got me thinking of the Van Hove model, because in algebraic quantum field theory, dynamics is basically implemented by net structures of algebras, etc. But really, if you look at the free field or the free field with some source term, the algebras and the net structures are exactly the same. And it's just the sort of what you sort of pick as the generators of your algebra, or so in a sense your basis, in a loose sense, that really distinguishes these theories. And I was wondering if that is sort of the same thing that you are describing here, but just in different formalisms.
I think so. I think that is exactly one of the that is the analog, one of the analogs in algebraic quantum field theory on curved spacetime to the issue here. That insofar as, I mean, there's an issue. There's a prior issue. I mean, it's funny. It's even hard. It's hard to talk about here because it's not even clear what one means by evolution, dynamical evolution in this context.
No.
To start with, it's really hard to try to even begin to start to impose your classical prejudices and your classical ideas about interaction and evolution in the context. Insofar as one can do it, the claim you just made, I think, perfectly encapsulates the idea that there is no real distinction, that the algebras for the free field and the algebras for the interacting field are the same algebras. So I think that is exactly one of the analogs for the kind. That's exactly the kind of thing I want to say reflects the same conceptual state of affairs as I tried to describe in the non-relativistic regime.
That being said, if you add some friction term to your Klein-Gordon equation, so something of well, only dt5, for instance, that does change the algebra. So yeah, I mean, that is not, that sort of is different from the situation that you sketched in your talk. So,
well, that's because you're dealing with a different kind of physical system at that point. So that's quite natural. That's like saying that'd be like saying, well, you know, I'm talking about a system with one billiard ball versus a system with a pool table with one billiard ball versus a system with a pool table with two billiard balls. They're different physical systems.
Okay, yeah,
Of course
sure.
they have.
Okay, thank you.
Okay, so before I return to Jacob and his myriad questions, Richard, you had put a question in the chat. I didn't know if you wanted to ask it, or if anybody else has any.
Oh, well, I think Jacob already answered that. It's the source terms, J and rho, were also similar to the in derivative terms for things like a displacement current. If I just would read the way the derivatives on the left-hand side of the Maxwell's equations were being written.
Okay, so final call for other questions before we return to Jacob. Okay.
And by the way, I mean, it is pretty close to 11:30. So if, for example, you'd like to end the recording and formally end the meeting, I mean, if Erik is game for chatting a little bit after the meeting, we don't have to keep everybody unless people are interested in sticking around.
Well, I'm happy to keep the meeting running and recording. I'm sure that your conversation will be interesting as long as you're okay with that.
Well, I foolishly claimed at the start that I would be happy to go on as long as I wanted, but I'm still recovering from a sinus infection, and I'm actually flagging pretty seriously. So I think I might actually request, Jacob, that we take this offline, and I would love to talk with you about it. So let's email and set up a Zoom conversation if you like.
That'd be great. Thanks.
Okay, well, thank you again to Erik. This has been fantastic.
Thank you guys for the fantastic questions and letting me get this off my chest.
And I hope to see all of you again next week.
Take care.